Okay, I've graphed it. I don't see everything. I'm going to increase the window. I'm going to go all the way up to 200. Whoop, that's my X. We'll go down to negative 200 and up to positive 200. See what kind of graph we get then. That actually looks pretty good. I'll just change it one more. I'll go to 300. It looks like negative 300 and positive 300 will give us a great graph. I'm going to change my scales to 100 so I don't see so many of them. And I have a general graph shaped right there. Good. Now, the way that your calculator does that is it generates a ridiculous number of points and plots them in pixels on your calculator. You can see the pixelated pieces on your calculator, which help generate the graph, and that's how it plots it. We are going to be able to do that through knowledge of calculus, which is extremely interesting and very good stuff. Now, here's what I need you to learn today is the first derivative test. If I took the first derivative of this point right here that I'm pointing to on this graph, would it be positive or negative? Positive. Is the graph going up or down? How about the derivative here? Positive. The graph is going up or down? How about here? The graph is going down. It's negative. The first derivative tells us this, if the function is increasing or decreasing. The second derivative tells us something else, okay? Just to give you guys a hint, the second derivative tells us this, okay? See how this is like an upside down shaped parabola? That's what we call concave down. And then see how this part is a parabola that looks like it's right side up? That would be called concave up. Second derivative tells us what we call concavity. And it changes at a certain point, which is called the inflection point. Today, we only want to look at this first thing, which is increasing and decreasing. Now, you guys can point to the spots on the function where it's increasing and decreasing. It looks like it's increasing all the way up to this point of this local max, and then decreases all the way until we get to this point of this local min, and then increases after that. We want to verify that and justify that through the nature of algebra and work from there. So now that we have a picture of it in our minds, let's actually go about working through this piece. I'm just going to sketch a little graph right there just to keep it in mind of what that actually looks like, okay? And it says as follows. For the following functions, identify the intervals on which the function is increasing and decreasing. Also identify the local minimum and maximums. In order to find points of interest for increasing and decreasing, I have to first find all of the critical points. In order to find the critical points, I identify where either the function is undefined. Is it undefined anywhere? No. Is it ever not differentiable? No. And then the last place would be wherever the derivative is equal to 0. What is the derivative of this function? (6x² minus 6x minus 72). That's the derivative. In order to find the critical point, I set that equal to 0. 0 equals 6 times x² minus x minus 12. Pauline just sent me a text. Sent me an email. You can expect a text later, and it will be horrifying. And I will make fun of, yeah. What class do you have 7th hour? Actually, I'm giving you a test 8th hour. 8th hour, I'm giving you a test, so I'll be sitting at my computer. I will send you no less than 400 texts. Wait till you get. That's all I'm going to do. That's all I'm going to do this whole time. All right. Oh, she's so funny. Okay. All right. So if I factor this, I get 0 equals 6 times x minus what? 4 times x plus 3. So it looks like I have 2 critical points here. All right. I have 2 critical points. Now, I've already given you guys somewhat of an organizer here, and I encourage you to do something like this. You don't have to actually draw the grid, but to help organize our data. In order to test to see where this function is increasing or decreasing, I break it up into certain intervals. The intervals change at the critical points. So we have one interval, which would be from negative infinity to negative 3. We have another interval, which would be from negative 3 to positive 4. And we have a last interval, which would be from 4 to positive infinity. Sorry, Stuart, infinity. Yeah, infinity. All right, up here, I'm going to put the factors of the derivative. Now, note that you do have to account for the negative. If you have a negative out front, we have to account for that as well. Is there a negative out front? No, so I could simply just write x minus 4 and x plus 3. And then what we do is we test points to see whether the derivative is positive or negative over those intervals. What is a point? What is a point between negative 3 and negative infinity that you would like to test? Let's try negative 4. Negative 4 minus 4, positive or negative? It is negative. We are testing to see whether the derivative is positive or negative, whether the function is then increasing or decreasing. Negative 4 plus 3, negative. So if you look, if I were to multiply out the derivative, 6 times a negative is a positive. So that tells me that f prime of x is positive over that interval. If f prime of x is positive, that means that the function is increasing. Question. Yep, I picked a number between negative infinity and negative 3. What would be a good number to choose between negative 3 and 4? I choose 0. If I plug in 0, 0 minus 4 is negative. 0 plus 3 is positive. So note that I have 6 times times a negative times a positive will give me a negative. So between negative 3 and positive 4, the function is decreasing. The function is on its way down. Okay? And then between 4 and positive infinity, what I have here is, what's the number you'd like to check? We'll try 5. 5 minus 4 is positive. 5 plus 3 is 6 times a positive is positive. So we have now identified for this function the intervals on which it's increasing. Where is the function increasing? Negative infinity, negative 3. Where else? 4 to infinity. Where's the function decreasing? From negative 3 to positive 4. Now, I do have a local min. Will the local minimum happen where the function goes from decreasing to increasing, or where it goes from increasing to decreasing? Yeah, if you look at your function right here, the local minimum happens where it goes from negative to positive. Where does it go from negative to positive? The derivative goes from negative to positive at the point 4. So 4 is where we have our local minimum. So we'll say f of 4 is, and we would plug 4 in. If we plug 4 into our table, yep. My calculator is freezing up. I'm having smartboard problems. Wait, what is it? Okay. The local maximum will occur where the derivative goes from increasing to decreasing. The derivative goes from increasing to decreasing, positive to negative, at the spot -3. So f of -3 is equal to 135. So we found a local min, we found a local max, we found the areas on which it's increasing and decreasing. This would give you a very good sketch of the graph. The last thing we could do if we wanted to find a sketch of the graph is we could look at our original function and find all the zeros. Now, have you done that before? That was back at pre-calculus. So we could generate a really, really, really good sketch of this graph if we wanted to find those zeros as well. Because we know the heights of the local min and maxes, and we know where it's increasing and decreasing. Okay? Any questions on that first example? Question? Yeah. A maximum occurs where the function goes from increasing to decreasing, where the function goes from a positive derivative to a negative derivative. So my derivative went from positive to negative at the point -3. So therefore, that must be my maximum at -3. The function went from decreasing to increasing, which tells me I have a local minimum at the point +4. So that's how I figured it out. That change is what happens. Just because I have a critical point does not mean I have a local max or min, which you'll see in this next example. We'll do one more together. You guys can work on the back side then. Same type of problem. I start out by finding the critical points. In order to find critical points, I look where the function is undefined. Is it undefined anywhere? It's differentiable everywhere, so in order to find the remaining critical points, I take the derivative, and I set it equal to 0. What's the derivative? -4x to the third plus 12x squared. If I set it equal to 0, I get -4 x squared times x minus 3. Yep. So what are my critical points? Whoop. So 0 and 3 are where something interesting happens. Okay? And we'll find out more about that. 0 and 3 is where something interesting happens. So we're going to divide this up into certain intervals. The intervals which we'll divide it up into is from -infinity to 0. What would be my next interval? 0 to 3. My third interval? 3 to infinity. Now, you guys, I told you, yeah, I told you guys that, you know, we just have the 3 intervals. You could have situations where you have 4 intervals, or you could have situations where you just have 2. So it's going to be up to you to kind of, you know, figure that out. Okay? So my factors that exist, I have to account for my negative. The negative will be very important with the process because obviously that causes for a sign change. So you can't just write -4x squared here. You got to write, or you can't just write 4x squared. You have to write -4x squared. And then we have x minus 3. And we're going to start testing points to see if it's positive or negative. Note that you guys knew more in general the first one because we graphed it. We saw what it looked like. But who knows about this? We haven't seen what it looks like yet. You might have a general idea, but we're wondering. So we're going to test points. What point would you like to test for the first one? -1. Sounds good. -4 times -1 squared, is that going to be positive or negative? It's going to be negative. -1 minus 3, negative. And a negative times a negative is positive. So it looks like it increases right away. Starts out by increasing. 0 to 3, what point would you like to check? -4 times 1 squared. Negative. 1 minus 3, multiply. So was there a sign change yet? No. So just because we have a critical point does not necessarily mean we have a change in between increasing or decreasing. You'll understand when we actually view the graph. 3 to infinity, let's plug in 4. Positive or negative? Negative. 4 minus 3. Positive. Multiplying, you get negative. Very good. So intervals of increasing are going to be from negative infinity to 0 and from 0 to 3. Intervals of decreasing, 3 to infinity is where it's decreasing. Now, again, local max occur where it goes from increasing to decreasing. Does it ever go from increasing to decreasing? At what point? 3. So you looks like you have a local max at f of 3. The local min is when it goes from decreasing to increasing. Does it ever go from decreasing to increasing? So we have none as far as local mins are concerned. Now, let's look at the actual graph to verify whether or not we did this correctly. If we go into y equals and we type negative x to the 4th plus 4x to the 3rd, and we graph that, I'm going to change my window because it's way out of whack. There we go. Do you guys see what happens right there? There's a triple root at 0. So there's no local min or max. It simply flattens out at that one spot. So is it truly increasing from negative infinity to positive 3? Yes. And then after that it goes down. So it looks like my graph is entirely, it looks like all my data fits that graph 100%. This is correct. The last thing I'm going to do here is I'm going to actually go into my table and I'm going to calculate that value at 3. And it reaches a, why won't it do it? Oh. If I punch in 3, I get a value of 27. So the local max is 27. It has no local mins. Finding that information out will allow us to draw a better sketch. On Monday, we'll talk about concavity. And note that we're dealing with very nice functions. We'll get to the not so nice ones later. Okay, you guys can go ahead and start the back side there.